Hi everyone. In the last session, we have started the topic called number system. In that class, we have defined that a number system is used to represent a certain quantity. And we discussed there are various types of number systems. The first one we discussed is the decimal number system, and second one is the binary number system. Third one is octal number system, and the last one is hexadecimal number system. And we know the base for the decimal number system is 10, and the base for the binary number is 2, and the base for the octal number is 8. And we discussed that the base for the hexadecimal number system is 16. In the continuation of the last session, where we have completed how to convert a decimal number system into the binary and binary number system into the decimal. Now, in today's session, we are going to talk about how to convert the remaining number systems into another number system. That means we are going to talk about how to convert the decimal number system into octal or octal to decimal, or we can say octal to binary, hexadecimal to binary, and binary to hexadecimal, vice versa. That we will see in detail in today's session. Let us take one number, any decimal number you can take. Assume that I'm taking the decimal number 523. This is the decimal number. You can write the base 10 or you may not write the base 10, but better to write the base 10 to indicate the decimal number. 523 is the decimal number. Now, how to convert this decimal number into octal? I said that the octal number system base is 8. That means we are going to have the digits from 0 to 7. How to convert this into octal? To convert this number into octal, what we have to do is, in the yesterday's session, I said that if you want to convert the same number 523 into binary, then we have divided that number with 2. But here, to convert this 523 into octal, we have to divide the same number 523 with the base 8. Now, how to convert this decimal number into octal? Take the number 523, right? Now, divide with 8. 8 6 are 48. 8 6 are 48. The remainder is 4. Means we are getting 43. 8 5 are 40. The remainder is 3. After this, you write 8 8 is 64. The remainder is 1. And 8 1 is 8. The remainder is 0. Now 8. So you can divide 1 with 0. 8 0 is a 0. Then the remainder is 1. Now, as I said, to represent the octal equivalent for this, you come from bottom to top, means 1013. That means the equivalent of the decimal number 523 in octal is 1013. This is octal 1013. This is how to convert the number 523 decimal number into the octal number 1013 base 8. If you want to verify the answer whether it is correct or not, then what you do is just take the number in octal and convert into the decimal. Now, how to convert this octal number into the decimal, that we are going to see. So here we are converting the decimal number into octal. Now, to verify the answer whether it is correct or not, next we are going to convert octal into the decimal. How to convert the octal into decimal? I think we got the answer 1013, right? 1013 is the octal number, and now we are going to convert into the decimal. Now, how to get this decimal number? As we have seen in the yesterday's class, how to convert the binary into equivalent decimal. Then here what you do is take the octal number here 1 0 1 3. Now from the right to left, what you do is you take 8 to the power of 0, means the 3 is at unit position, 8 to the power of 0, next 8 to the power of 1, 8 to the power of 2. Why we are taking 8? Why? Because the octal number base is 8. Here 8 to the power of 3. Now, just find out the results. 8 to the power of 0 is 1. 1 into 3, 3 plus 8 to the power of 1, 8. 8 into 1, 8 plus 8 to the power of 2, 64 into 0, 0. And here, 8 into 8 and 64 into 8, how much? 64 into 8. 8 4 is 32, okay. 8 6 is 48. This is 512. Okay, 512. This is 512. Now, the result here, how much we are going to get? 523. You see this. This is the decimal equation. I think we got the same answer, 523. This is the way to convert the octal number into the decimal. Now we will see how to convert the octal number into binary. There are two approaches for this. Let us discuss those. See, whenever you want to take a number, for example, if you take the number 28, if you take it as the base 8, this is not valid. Why it is not valid? Why? Because the octal number base is 8, but the digits that are valid is only from 0 to 7. When the digits are only in between 0 to 7, you can't take 8 here. That's why this is wrong. Take the number 27. It's valid. The base is 8. Now, how to convert this 27 octal number into binary? There are two procedures for this. The first thing is take this octal number and convert into the decimal. Convert this into decimal. How to convert into decimal? Take the number 27 like this, and you take 8 to the power of 0, 8 to the power of 1. Here, this is 1 into 7, 7 plus 8 to the 16. Now, the decimal equivalent we are going to get is 2310. Now, take the number 23 and now convert into binary. That means 2 10 ja, 2 1 ja 2, 2 1 ja 2, the remainder is 1. 2 5 ja 10, the remainder is 1. 2 2 ja 4, the remainder is 1. 2 1 ja 2, the remainder is 0, and it is 0 and 1. So here we are going to get 1 0 triple 1. 1 0 triple 1. This is the binary equivalent. This is the binary equivalent of the number 27. Directly we have done? No. We have taken the octal number and we have converted into decimal. The decimal equivalent is 23. After for this, we are converting into binary and the result is this. This is the one approach. The second approach is just you take the number 27. This is the direct approach, octal number. Now you take the first digit and second digit individually, and you take the binary equivalent of 2 and 7. The binary equivalent of 2 is 1 0. The binary equivalent of 7 is 111. You see this. Same result we are getting. This. Both are same. This is the direct representation and this is the indirect representation. This is the way of how to convert the octal number into binary. Right? For example, you want to convert the same binary number into octal. How to take the number direct conversion? See here, we got the number. The number we obtained is 10111. This is the binary equivalent. Now, how to convert this into octal direct approach? So to convert this into octal direct approach, what you do is you divide the entire bits into groups, and each group is going to contain 3 bits. So here 3 bits are there, here only 2 bits, just you add 0, no problem. 0, 1, 0 and 111. Now, 111, what is the equivalent of decimal equivalent of 111 is 7. What is the decimal equivalent of 0102? 27. This is the way of getting the octal number 28 from this binary equivalent. What is the indirect approach? Take the same number 010111 and you convert it into the decimal number. From the decimal also you can go to octal. Both are valid. How to do this? Just you take 0, what is the value you have? 1011. Just you take this binary number and you convert into decimal. 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and 2 to the power of 4. Now here we are going to get 16 plus 4 plus 2 plus 1. We are going to get 23 is the decimal number. Okay. Now from this 23, convert into octal. 23 is the decimal number and you convert into octal. What do you do? To convert this decimal number into octal, you divide with 8. 8 2 just 16. 8 2 just 16. The remainder is 8 2 just 16. 8 2 just 16. 16 means 8 2 just 8 3 just 24, right? 16 means now how much? 8 2 just 16. Here we are getting 7, right? Now 8 0 is 0. Remainder is 2. So here you are getting the number 27. This is octal. This is the way of performing octal to binary and binary to octal. We have the direct approach at the same time. the indirect approach. Similarly, you can also go for the hexadecimal number system. Hexadecimal number system. I said that hexadecimal number system is going to take the base 16. That means the values we are going to get is 0 to 15. That means 0 to 9. Another one is from A to F. This is the base 16. For example, I'm taking the number 1AF. What is 1AF? AF we are using, so this comes under the hexadecimal number system. Now, how to convert this into binary? For this, we have the direct approach, at the same time indirect approach. What is the direct approach? Take the number, each number like this, and you convert into the binary. But here, at a time, you have to take 4 bits. So 1 is denoted by 0001, and A is nothing but 10. A is 10. A is 10. So here the 10, right? Binary equivalent of 10 is 2 5 is 10, the remainder is 0. 2 2 is 4, the remainder is 1. 2 1 is 2, the remainder is 0. Here it is 1010. Here we are getting 1010. So you take each digit and you convert into binary equivalent, right? But each group pattern should consist of 4 bits, right? 4 bits I'm taking. Now F is 15. Can If you take 15, 2 7 is 14, 1, 2 3 is 6, 1, 2 1 is 2, 1. So here we are getting triple one, 4 ones, sorry, 4 ones. So 4 ones is the binary equivalent of F, and 1010 is the binary equivalent of A, and this is the equivalent of 1. This is the direct conversion from hexadecimal to the binary. So from this binary to hexadecimal also, you can take the bit pattern and you take 4 bits at a time and you convert into decimal directly, so that we are going to get hexadecimal number. This is the direct approach. What is the indirect approach? First, take this hexadecimal number and you convert into, what do you say, decimal number. How to convert 1 AF is the hexadecimal number. So how to convert this decimal? From the decimal, you can convert the binary. So if you want to convert into decimal, just same procedure. You take AF and you take 16 to the power of 0 and 16 to the power of 1 and 16 to the power of 2. So that we are going to get some decimal value. For there, after taking this decimal value, to convert into binary. So these are the different approaches by which we can convert one number system into another system. So these are the basic fundamentals you must know before applying the bitwise operators. Now we will discuss the bitwise operators one by one. Now we are going to start bitwise operators. Why we are calling these operators as bitwise? Why? Because they will operate at bit level. What do you mean by bit level? See here, for example, if you take any value for the variable, for example, a equals to 7 and b is equals to 8. 7 is in decimal number system. Even though I didn't mention any base, it comes under the decimal number system. And 8 is also a decimal number system number, right? Now, if you perform the bitwise operation on A and B, internally they are converted into bits and final result is shown in the decimal number system. See, so we will see one example for this. But before moving on to the operation, let us discuss how many types of bitwise operators are there. We have bitwise AND. The first one we are talking about is bitwise AND. This is denoted by the symbol AND, ampersand, right? See here, this is not an address operator, it is only the binary operator, right? Bitwise AND, that is ampersand, is binary operator, means it is going to operate on 2 operands. After bitwise and second one we are going to take is bitwise OR. Here we are going to take the symbol, pipe symbol, and third one is bitwise AND, bitwise OR, and bitwise exclusive OR. This is denoted by this symbol, caret symbol, right? And fourth one we have bitwise AND, bitwise OR, bitwise exclusive OR. We have bitwise NOT. This is represented by the tilde symbol. We call it as TILD, tilde symbol. Now after fourth one we have bitwise left shift. This is left shift. We call it as bitwise left shift. After this, we have sixth one, bitwise right shift. Bitwise right shift. Right shift. This is denoted by double greater than, and this is denoted by double less than. These are the various bitwise operators. We are going to discuss each and everything with an example. Let us discuss the first one, bitwise AND. We're talking about bitwise AND. Bitwise AND operation or operator is denoted by this symbol. Let us take at Python shell, assume that we are taking a is equals to, assume that 11, and at the Python shell we are taking b is equals to 7. Now here at the shell, if you say a and b, what could be the result? That we are going to see. As I said that it takes the input in the form of decimal number, but and also the output we are going to obtain is also decimal number, but the internal operation is done at bit level. So what does it mean? Now actually, to get the result of this, first internally what happens, it is going to take the number 11. 11 is going to convert into binary first. Here 2 5 is 10, the remainder is 1. 2 2 is 4, the remainder is 1. 2 1 is 2, the remainder is 0. Here we are going to get 1011. 1011 is the binary equivalent of 11. Next, if you take 7, the binary equivalent of 7 is 2 3 is 6, 1, 2 1 is 2, 1. So here triple 1. We are going to get the binary equivalent of 7 is triple 1. This is the binary equivalent. See here we have 4 bits and here we have 3 bits. So if you add 0 extra here, no problem. So that first number 11 is also going to contain 4 digits and 7 is also going to contain the same number of bits. If you add zeros to the left, no problem, it will not affect anything. So 1011 and it is the binary equivalent of 11 and 0111 is the binary equivalent of 7. Now 1011 after that 0111. This is the bit level operation. Now after performing into bits, now you apply the operator AND. This is logical AND. So logical AND, what it is going to do, if both bits are 1, then only the result is 1. In any other case, the result is 0. Very, very important. In both the bit patterns, if you get both the bits 1, then only the result is 1. In the remaining case, the result is 0. That we are going to obtain. 0011 is the result. Okay, that means when you apply this bitwise AND, 01 becomes 0, 10 becomes 0, 00 becomes 0, only 11 becomes 1. Okay, so in this case we are getting 011. After getting 0011, this is the bitwise pattern or bit level representation. Now this bit level representation, or we can say the binary number system, is again converted into the decimal number. That means 0011. Now this 00, so say take, like I said, no, how to convert this binary equivalent to decimal, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. So what is the result we are going to obtain from this is 3. So the result we are going to obtain is 3 after performing this operation A and B. We are going to get 3. This is a way of using the bitwise AND. Now for the same number, for example, here we are going to get 1011 and the number is 0111, 0111. This is first one is 11 and second one is 7. Now we are going to apply next second operator bitwise OR. This is bitwise OR. Here I am applying bitwise OR. So what the bitwise operation is going to do is, if any bit is 1, this is the first bit pattern and this second bit pattern. See for the OR operation what happened. If you get 0 1, the result is 1. 1 0, the result is 1. 0 0 is 0. 1 1 is also 1. If any one bit is 1, the result is 1. Okay, so this is about the OR operation. So now 1 1 1 1 1 1 0 1 1 1 0 also 1. So this is the result we are going to obtain after performing the bitwise exclusive OR. And here we got 4 ones. 4 ones, the decimal equivalent is 15. The answer we are going to get whenever you say A or B. A is 11, B is 7, A or B, the result is 15. Okay, how the result we get 15? This is the binary equivalent, right? So we are converting this binary equivalent to decimal, the result is 15. This is about bitwise OR operation. After bitwise OR, next we have bitwise exclusive OR. Same thing, it is similar to OR. The only thing is, please remember, if the first two bits are 0, 0, it is 0 only, 0, 1, 1 only, 1, 0, 1 only. But whenever we get both bits are 1, the result is 0. This is exclusive OR. Exclusive OR mostly equals to OR, but whenever we get two bits 1, the result is 0. Now, if you take same example 1 0 1 1, 1 0 1 1, this is 11, and 0 1 1, this is 7. Now, whenever you perform this exclusive OR operation 1 1 0 1 1 0, this is 1, this is 1, 1 1 0 0. What is the value of 1 1 0 0? The value of 1 1 0 0 is, right, 2 to the power of 0, 2 to the power of 1, to the power of 2, to the power of 3. Just you convert into the decimal equivalent. Now we are going to get 8 plus 8 plus 4. 8 plus how much? 12. The answer we are going to obtain is 12. 12 is the decimal equivalent of 1 1 0 0. Okay, double to the power of 2, right. So this is how the exclusive OR operation is performed. Next we will see bitwise NOT and bitwise left shift, bitwise right shift. Now we are going to see the next bitwise operator called bitwise NOT. We are going to talk about bitwise NOT. It is represented by the tilde symbol. Actually, the meaning of this bitwise NOT is called ones complement. We call it as ones complement. Now, what it is going to do? What is the result we are going to obtain when you apply the operator bitwise NOT, or we can say ones complement? Let us take one example. At the dollar prompt, you take the value A is equals to 11. A is equals to 11. Now, if you say ones complement of A, or we can say not of A, now what is the result we are going to obtain? What could be the output? Or what you say, what would be the output that we are going to discuss? See what happened. First, take the number 11. Okay, we are taking the number 11 and it is converted into its bits representation. That we know that 2 5 is 10, the remainder is 1. 2 2 is 4, the remainder is 1. 2 1 is 2, the remainder is 0. Here we are going to get 1 0 1 1. 1 0 1 1 is the binary equivalent of 11. Now, whenever you use the bitwise NOT operator, carefully remember that after getting the number 1011, take extra bit for representing the sign bit. If the leftmost bit is 0, it indicates positive number. Okay, if the leftmost bit is 1, that is, so we are using 0 for representing the positive number and 1 for the negative number. We have taken only the positive number 11. Its internal representation is 1011. Extra we are adding 0 to indicates that this is the positive number. Okay. Now, after that means this number is changed to 0 1 0 1 1. Right. Now, what this operator is going to do is this ones complement operator converts every bit of this bit pattern from 0 to 1 and 1 to 0. That means this 0 is changed to 1 and this 1 is changed to 0. This 0 is changed to 1. Okay, this one is changed to 0 and this one is changed to 0. So what is the result? We are obtaining 1 0 1 0 0. This is the result. Okay. Now I said that just now the leftmost bit represents this sign. leftmost bit is 1 here. That means we are going to get the negative number. Now, what is the negative number? What would be the negative number? See, the output here we are going to get is, just you do one thing. So like previous example, you convert this binary equivalent into the, what do you say, decimal number. Generally, what we are going to do, we are taking 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. But important thing you must identify here is the last leftmost bit is 1. See, whenever you take the positional weight for this number, 2 to the power of 3 and this is 2 to the power of 4. But the thing you have to do is, it is the negative, the sign is minus. So, minus 2 to the power of 4. This is the value we are going to obtain. What is the value? Minus 2 to the power of 4 means how much? Minus 16, leftmost value. And you know, 2 to the power of 3 is 8 into 0, 0. Just you can calculate the result from right to left or left to right, no problem. Here just I'm moving from left to right. So this value is minus 16. This anyhow it becomes 0, and this is 2 to the 2, 4 into 1, 4, minus 16 plus 4, and this becomes 0. The remaining all values are 0. So minus 16 plus 4, here we are going to get the result is minus 12. After applying this ones complement of A or bitwise not of A, when A value is 11 in decimal, the output we are going to obtain is minus 12. This is very, very important, right? Ones complement of A or bitwise not of A is minus 12. This is the way of getting the result when you apply this ones complement or bitwise not. Now, we are going to talk about bitwise left shift operator, that is indicated by this symbol, bitwise left shift. Take any number. For example, here we are taking A is equals to 10. 10, what is the binary equivalent? 2 5 are 10, the remainder is 0. 2 2 are 4, the remainder is 1. 2 1 are 2, the remainder is 0. Here we are going to get 1 0 1 0 1 0 1 0. This is the, what do you say, the binary equivalent. If you want to add the to the left as the number extra bit 0 to represent the sign, you can add it. Okay, 0 1 0 1 0, no problem. Now, when you apply the left shift operator like this, for example, A left shift, assume that I'm using the number 2. How many bits I'm going to shift to the left? This 2 bits I'm going to shift the bits to the left. See, when we are shifting the leftmost 2 positions to the left, so right side we are going to get 2 empty bit positions. That means this result, whenever you shift 2 bits left, what we are going to get? To the right, we are going to get some empty bit positions 0 1 0 1 0. These bit positions are replaced with zeros. So now we are getting the result like this 0 1 0 1 0 0. Now you take the equivalent decimal value 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 3, and 2 to the power of 4, 2 to the power of 5, 2 to the power of 6. Just I'm going to take the values whose bit positions are 1. This is 32 into 1, 32, plus this is 8, plus all are 0, right? Just the value we are going to get is 40. Now, after performing this left shift operation with the number of bits that are shifted is 2, then we are getting the result 40. Okay, so this is the way of calculating the result. So instead of doing like this, directly you can expect the answer 40 by using a principle like this. See here, the original value 10, right? A value is 10. Now, how to get this 40 directly? When the value is 10 and when you are shifting the number of bits 2, the base of binary number is 2, just I'm taking 2. How many bits you have shifted here? 2. Number of bits shifted is 2. See, the left shift operation result is based on, take the original number 10 and it is multiplied with the base, the binary base is 2 and the number of bits that are shifted is 2. That means 10 into 4, 40. This is the direct way of verifying the answer 40. Instead of taking 2, if you take 3, that means 3 position at a time we are shifting the 3 bits to the left. In this case, what happened? Just you write the result is the 10 into 2 to the power of 3. That means 10 into 8. The answer we are going to obtain is 80. This is how the left shift operator is going to work. So in the left shift operator, just we are taking the number and we are multiplying with the base 2 power of number of bits shifted. If it is the right shift operator, instead of multiplying, we are going to divide it. We will see for that. And just now I said A is equals to 10, and I said the binary equivalent is 1010. Okay, this is 1010. If you apply at Python shell right shift operator 2, so the result what you are going to obtain is 10 by. Previously we have multiplied, now we are going to divide 2 to the power of 2. That means 10 by 4. 10 by 4, we are going to get 2 point something, but you take only the integer part 2. The answer is 2. 10 by 4. Don't take the fractional part, just you take only the integer. That means we are performing the floor division. We are getting 2. So after performing this operation, the output we are going to get in decimal number is 2. Let us see whether it is correct or not. So the bits are 1010. Okay, 1010. You can add extra bit 0. That's your wish. Now we are shifting this to the right. How many bits? 2 bits. We are shifting these 2 bits right. There is no space to the right. That means these 2 bits simply discarded. These 2 bits simply discarded. Now we are getting 0, 1, 0, the remaining bits. The left side 2 bit positions are added with 2 zeros. So 0, 0, 0, 1, 0 is the answer. The binary decimal equivalent of this binary is 2. That's why we are getting the answer 2. This is the way of performing the right shift operation. This is very, very important. Now, this is about the positive numbers. So what about the negative numbers? If you take, for example, if you take the number a is equals to, assume that minus 10. And now we are going to perform the shift operation a. You can use right shift or left shift. Here I am using right shift. Just now I said that to verify the answer, to directly get the result, what you do is, when it is the right shift, I said that minus 10 by 2 to the power of 2. That means minus 10 by 4. The result you are going to get is minus 2. Minus 10 by 4, that is we are going to get minus 2. How you are going to get minus 2? We will see here. How we are going to get minus 2, minus 10 by 4? How we are going to get this answer? Let us verify this. See, what the value of a is minus 10. What do you mean by minus 10? Actually, minus 10, or we can say the negative numbers. Very, very important thing you should note here is the negative numbers are represented by using 2's complement. This is very, very important. Minus 10 is nothing but 2's complement of 10. Now, first you take 10. 10 we know that 1010. Extra you take 1 bit for what do you say, sign. This is 10. Now, first find out the 2's complement of this. How to find out 2's complement? First find out the 1's complement of this. 1's complement. What is mean by 1's complement? Just change 0 to 1 and 1 to 0. Here we are going to get 1 0 1 0 1. This is the result we are obtaining after performing 1's complement. To get 2's complement, what you do is, after obtaining the 1's complement, just you add again 1. 1 plus 1 0, 1, 1 plus 0 1, and here we are getting 1 0 1. 1 0 1 1 0. 1 0 1 1 0. This is the result. Now what is the result we are getting? 1 0 1 1 0. This is how we got the 1's complement, sorry, 2's complement of 10. This is 2's complement. 1 0 1 1 0 is 2's complement. After obtaining this 2's complement, now the shift 2 bits to right or left? Right. So these 2 bits are shifted right. Okay. these two bits are discarded. Now the left side we have 101. 101. What about this bit? The leftmost bit is sign bit, right? It is sign bit. So the sign bit is not changed like this. See here, when we discard right side 2 bits, we are going to get left side 2 bits vacant. That means 101 remains, left side 2 bits are vacant. Now here, instead of adding 00 to the left, what you have to do is, already the leftmost bit is 1, it indicates the negative sign. So when it is negative, when it is 1, the remaining 2 bits are also filled with the sign bit 1. Now after performing the right shift operation for 10110, we are obtaining 11101, 11101, 11101, 11101. Now how to get the decimal equivalent of this? Just you do one thing: 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and 2 to the power of 4. I said that the leftmost bit represents the sign bit. For this, we are taking the value minus 16, and this is plus 8, this is plus 4, minus 16 plus 12, minus 16 plus 12, and last one, minus 16 plus 12, last one, 2 to the power of 0 is 1, 1. That means we are getting minus 16 plus 13. I think we are getting minus 3. See here, we have taken the number minus 10, right? We are dividing by minus 10 by 2 to the power of 2. That means minus 10 by 4. That means we are going to minus 2.5. But floor, it is going to take the result we are going to obtain is minus 3. Similarly, we are going to apply the left shift operator for the negative numbers. Same example you take. Let us assume that a equals to minus 10. Now, we are performing the left shift operation. That is a left shift. How many bits I am going to shift? 2 bits. Just now I said that whenever you perform the left shift, the answer we are going to get is minus 10 into 2 to the power of 2. That means minus 10 into 4. The output we are going to obtain is minus 40. Previously, whenever we take minus 10 by 4, instead of getting 2, we are getting minus 2, we are getting minus 3. Why? Because the fraction part is minus 2.5, it is rounded to minus 3. Now, in case of a left shift operator, left shift 2, the answer you should get is minus 40. Okay, we'll see how we are going to obtain this minus 40. See here, minus 10. Just now I said that minus 10 is nothing but 2's complement of 10. Just now I said 10 is nothing but 1010. Left side we are taking one extra bit to represent the sign. Now to get 2's complement of 10, first I am going to take 1's complement. After that we are adding 1 to 1's complement to obtain 2's complement. Now first convert this zeros into 1's and 1's into zeros. 10101. This is 1's complement. Okay, after getting this 1's complement, you add 1 to get 2's complement, right? 1 plus 1, 0, 1, 1, 1, 0, 1. 1 0 double 1 0. 1 0 double 1 0. 1 0 double 1 0. Now we are shifting how many bits to the left? 2. When the bits are shifted to the left, how many bits we are shifting? 2 bits. Then we are going to get vacant positions in the right. So those vacant positions are filled with zeros. That means we are going to obtain the result 1 0 double 1 0. Right side we are going to add 2 zeros, right? Extra 2 zeros we have added. This is about the left shift. Now to get the decimal equivalent, what we are going to do? 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, and 2 to the power of 6. The leftmost bit, as I said, it indicates the negative number. Means we are going to get the positional weight as minus 2 to the power of 6. Okay, next this becomes 0. Next, 2 to the power of 4, 16 into 1. How much? 16. 2 to the power of 3, 8 into 1. How much? 8. Remaining all are zeros. That means minus 64 plus 24. Minus 64 plus 24, how much? Minus 40. This is minus 40. But at the time of division, take the floor division. Okay, when it is 2.5 or more than 2.5, it is rounded to 3. That is very, very important. When it is less than 2.5, then it is going to round it to 2. This is how the left shift and right shift operators are going to work on the negative numbers. So with this, we have completed all the bitwise operators. Next class, we will see the assignment operators. So with this, I'm going to close the session. Thank you very much for watching.